Hello, this is Dr. Tammy Jovanelly, and I am excited to be here with you today because we are going to talk about the rock cycle. Hold your applause to the end. We are going to remember that we talked about minerals, and what we said about minerals is that a mineral is formed from different elements on the periodic table of elements. We defined two different groups. We said that there are silicates and there are non-silicate minerals, and we said that a non-silicate is when a mineral can stand alone. So we talked about carbon and nickel and zinc and sulfur and all the heavy metals. Gold is another example. So those are considered to be non-silicates. A silicate is when it has silica, Si, and oxygen, O, bounded together. And so a silicate is a strong covalent bond that forms 95% of the minerals that are found on the Earth's surface, the purest of which is quartz, SiO2. And you can have SiO2 is the root for silicate, and then you can have many other minerals bonded to it. So we can think about rhyolite or basalt or granite being other examples of silicate type of minerals. So the moral of the story is a mineral forms with the bonding of elements that we see on the periodic table. So our question that we start with today is, how is a rock different than a mineral? And by definition, a rock is naturally formed with a variety of different minerals composed in it. So we furthered that definition by looking at specific groups of rocks. This is the rock cycle. If there is a starting point to the rock cycle, it would be that body of magma that's upwelling to the mantle and into the continental crust or the oceanic crust. And that's where these mantle magma components are going to solidify. And when they solidify, they're going to solidify into an igneous rock. So the starting point is the magma as it comes to the surface and cools intrusively or it cools extrusively. In addition to an igneous rock, there's something called a sedimentary rock. So when you have the breakdown, weathering, and erosion by wind, water, glacial ice, it breaks down a rock into smaller pieces called the sediment. That sediment can then get lithified or cemented together to form a sedimentary rock. That sedimentary rock, you can add heat or pressure, or you can add heat or pressure to an igneous rock. Anyway, you bake it, and then it turns into a metamorphic rock through the process of metamorphism. So I introduced the rock cycle to you because we are going to explore in depth these three different rock types. It is a cycle, so you can bounce back from one location to the other. So if you have a metamorphic rock and you break it down into sediment, you can turn it into a sedimentary rock. If you have a metamorphic rock and you heat it too much, it turns back into magma and then can solidify as an igneous rock. So there, you can move around to different portions of the rock cycle. And it is the associated processes that are going to alter the rocks. So with an igneous rock, we talk about solidification. A sedimentary rock, we talk about lithification, which is compaction. And then with a metamorphic rock, we talk about application of heat and pressure, and that is called metamorphism. But don't worry about that too much because we're going to tease out that. But I just want you to recognize that a rock is composed of minerals, essentially, and these rocks are going to form under different scenarios that we will explore. We are going to start by talking about the formation of igneous rocks. And in order to do that, we have to introduce the Owens reaction series. You can applaud now if you want to. For Bowen? No? Fine. Okay. By definition, Owens reaction series determines the sequence in which minerals crystallize in a cooling magma. I love Owens reaction series, by the way. This is like mind-blowing stuff. Okay, so what you're imagining is this body of magma that's coming up towards the Earth's surface, and it's hot, right? So it might be even more than 1400 degrees C. So you have this body of magma, it's working its way up to the Earth's surface, and as it begins to cool, then different minerals are going to crystallize out of that body of magma. So when we look at Bowen's reaction series, you can see 1400 degrees, and you're imagining that's deep in the surface. You have all kinds of elements that are organized within that magma: silica, oxygen, magnesium, calcium, potassium. The list goes on. But as the body of magma comes closer and closer to the surface, you begin to crystallize specific types of minerals. So at 1400 degrees, you see the presence of olivine. Following olivine at 1300 degrees, you see pyroxene, amphibole, biotite is at 1100 degrees. And then moving closer towards the Earth's surface, and as that body of magma continues to cool, you see orthoclase, muscovite, and then eventually quartz, SiO2. So it shows you the temperatures at which these individual minerals crystallize out of that body of magma, knowing that these minerals can combine to form an igneous rock. And I'll give you examples of that. So Owens reaction series is broken up into two different branches that you can see on your screen. On the right, you see the continuous branch. And on the left, you see the discontinuous branch. The continuous branch is highlighting something called plagioclase. Plagioclase is another name for feldspars. And you have seen potassium feldspar in laboratory, perhaps. So plagioclase from 1400 degrees to about 1100 degrees can crystallize at really any temperature along that range. So from 1400 degrees to 1100 degrees, you can find any type of feldspar. Maybe it's more calcium rich if it crystallizes at a hotter temperature, or it can be more sodium rich if it crystallizes at a lower temperature. But the moral of the story is it's a range. On the discontinuous branch, it is showing you specific temperatures of crystallization. Thereby, olivine only crystallizes at 1400 degrees C, pyroxene at 1300, amphibole at 1200, biotite at 1100. And we can continue that discontinuous branch by saying that orthoclase crystallizes at 1000, muscovite at 900, and quartz at 800. So they crystallize at specific temperatures. So if you find a rock that has biotite in it, you know that that magma had to at least be 1100 degrees C. Fascinating, right? Because you're able to interpret the body of magma that this rock actually came from. In addition, there's two other terms on this diagram. The first one is called Mafic, and the second one is called Felsic. Mafic minerals are going to be those that have higher amounts of magnesium and iron and are typically dark in color. Oppositely, those that are felsic are going to have high amounts of silica. So silica, SiO2, the purest form of silica is quartz. You said it. That's right. So quartz is going to be your purest silica, and you're going to find it closest to the Earth's surface at 800 degrees C. That's one of the reasons why you can go to like any art show and they'll sell you those necklaces with like amethyst and rose quartz, because it's not expensive, because it's found all over the world close to the Earth's surface. So they are not considered a precious gem. They are abundant at the Earth's surface. So Bowen's reaction series is showing us how these minerals crystallize out of a body of magma. We can return to some questions that you will see on your exam coming up. The first one is, how do you interpret this diagram? Well, this diagram is showing you the rate at which minerals are crystallizing out of a body of magma. 2, what is the difference between the two branches? The rate at which they're cooling. The continuous branch is cooling over a range of temperatures. The discontinuous branch is cooling at specific temperatures. Mafic is silica poor. Felsic is silica rich. And what is the most stable mineral on this diagram? Well, obviously it's going to be quartz, because it's the purest silicate. These are all silicates on the diagram. It's the purest silicate, and it is the last to crystallize out of that body of magma. Now, we can also look at this diagram in an inverse fashion, where we can think about minerals melting. So if you have a rock and you increase the temperature to 800 degrees, quartz will crystallize out of that body of magma. The last thing that crystallizes out will either be olivine or plagioclase, calcium-rich feldspar. And we've already explained the idea of how does the Bowen's reaction theory explain the chemical composition of quartz? Well, you have a body of magma with all of these silicates in it. They're forming and crystallizing, but once that body of magma gets close to the surface at 800 degrees, the only thing left is going to be SiO2. Everything else is going to drop out. We can relate this to a igneous rock called granite that you might be familiar with. So like your granite covertops. Granite contains 3 different minerals. It contains biotite, orthoclase, and quartz. And so if I'm showing you a piece of granite and it contains these 3 different minerals, you can very quickly tell me the range of temperature that magma once was. So that the magma used to be between 1100 degrees C and 800 degrees C. And we know that because we can see evidence of these 3 different minerals within that body of magma. So Bowen's reaction series has proven to be a really useful tool to talk about the rate at which minerals form rocks. And so that leads us up to igneous rocks, because what we said is that igneous rocks form from the solidification of magma. So we looked at the rock cycle and we saw the starting point was magma coming to the surface and crystallizing. So Bowen's reaction series ties into igneous rocks. So my question for you is, when do you see magma on the Earth's surface? And of course, you see it on the Earth's surface when there's a volcanic event. So I'm showing you pictures from the 1980 Mount St. Helens eruption. You can see the eruption on the left, and then you can see what it looks like at modern day on the right. This was the last major volcanic event that happened in the United States. Mount St. Helens has been a little bit active from 2010 to 2020. We've seen a little bit of activity, and it is the volcano that's on watch within the United States for sure. Remembering that Mount St. Helens is over in Washington State, so over out there on the West Coast. So what we said is we see evidence of igneous rocks form from volcanoes. And so when we classify them, we talk about them being extrusive. And so that magma is coming to the surface and it's solidifying. And as it's solidifying, it cools quickly because it comes into contact with the air. So extrusive igneous rocks cool quickly at the Earth's surface. Volcano events give us an example of that. The other opportunity is for that body of magma to cool slowly within the Earth's interior. And so when they cool below the surface, they are called intrusive. And so you're imagining the magma slowly coming up towards the Earth's surface, and as it does, it's cooling slowly, and so it's allowed to grow bigger and bigger crystals. The question I have on the screen is, which type of igneous rock would be more helpful in describing the environment at the time of its formation? Which type of igneous rock would be more helpful in describing the environment at the time of its formation? So we're thinking in terms of absolutely dating a rock. So if we want to know the age of a rock, which igneous rock type would be more helpful in describing the environment at the time of its formation? And you at home said extrusive because it cools quickly at the Earth's surface. So as soon as the magma comes to the surface, it is solidifying, and so it's trapping that age date into its crystalline lattice. And we'll talk about how we actually extract that date later when we talk about absolute time. But the idea is it's cooling so quickly that we can get really good age dates from it. When we describe igneous rocks, we talk in terms of them being extrusive or intrusive, and that is going to dictate its texture. And so its texture has to do with the size and shape of the individual minerals that are within the rock. So these terms are just specific to igneous rock. The first one is called aphonetic texture. So an igneous rock that has an aphonetic texture is also called fine-grained. And so when you're looking at the rock, you're trying to identify the different colors that represents different minerals within the rock. And as an example on the screen is something called rhyolite. And so rhyolite, when you look at the rock, it looks like it's completely pink with just a tiny few specks of white and a tiny few specks of black. And when we link aphonetic rocks, usually what we find is that they are extrusive. So they're happening and forming from the eruption of a volcano. So if you find a piece of rhyolite, you're going to be looking around to see where did it come from, where was the volcano. And that's because extrusive rocks, when they come to the surface, they cool quickly, and so those individual grains do not have time to grow. Andesite and basalt are other examples of extrusive aphanitic rocks. Opposite of an aphanitic rock is something called phaneritic texture. And a phaneritic texture is a rock that has coarse grains. So in this situation, we link them to intrusive igneous rocks. So that body of magma is cooling slowly beneath the Earth's surface, and because it's cooling slowly, those individual minerals get to grow bigger and bigger. So when you look at the grains of something like granite, you're able to identify them with your own eye. So they're greater than 1 millimeter. So you can look at the pink, which is the potassium feldspar, the black is the biotite, and then you can look for the white being the quartz. So I just gave you a great tool to think about, because you're now able to identify these different environments of deposition just looking at these types of igneous rock. So now the next time you go to somebody's house and you see a granite countertop, you can tell them that it's phaneritic and it is an intrusive igneous rock that formed below the surface. And you're going to look like a rock star. You are. You're going to be really impressed. So we touched on these terms of Felsic and Mafic when we talked about Owens reaction series at the beginning of the lecture, but they truly are terms that we use to classify igneous rocks. And so on the screen, I have these definitions for you. Felsic rocks have high contents of sodium and potassium, and they also have high amounts of silica content, so greater than 50%. And we mentioned granite and rhyolite are both felsic. These rocks are usually pink, white, or light gray. And so your pink granites and your pink rhyolites are examples of rocks that are felsic. Opposite of that are those rocks that are mafic. So they have less than 50% of silica content, and they have much higher means of iron and magnesium and calcium. And so they're usually darker in color. We've talked about basalt representing the oceanic crust, remember? And we said that basalt has a really high density. It's a density of 3.3 grams per cubic centimeter. So basalt is considered mafic. It is considered aphanitic. And we compared that to continental crust, which was granitic. And we said that granitic crust was lighter at 2.7 grams per cubic centimeter. And granite is intrusive and phaneritic. So we can make these relationships of their texture. Once in a while, you can end up with an intermediate type of igneous rock. It's not often that you find this, although sometimes in Iceland you do see it. And this is when you have equal amounts of silica and ferromagnesium minerals. So in lab, you might see something that's called diorite, and we call that diorite Dalmatian because it's black grains with white grains, and there's equal portions of each, as you can see on the picture on the screen. So we use these terms to explain how igneous rocks are formed, but it's common to have rocks that form in different environments that have the same mineral composition. Granite and rhyolite are examples of that. So granite is a phaneritic, intrusive, felsic, igneous rock. Rhyolite is an aphanitic, extrusive, felsic, igneous rock. So the term felsic is describing the mineralogy. And rhyolite and granite happen to have the exact same mineralogy, but they form in different locations. So rhyolite is forming outside the volcano, and granite is forming in the interior. And we said that when we looked at Bowen's reaction series, remember we talked about the crystallization temperatures, we outlined biotite, feldspar is also called orthoclase, and we looked at quartz. And that's what you're seeing on the screen here. So you're seeing those in a variety of percentages that is represented of these two rocks. So what I wanted to do for the last remaining bit of lecture is just to identify some different structures. So the first one is highlighting an igneous structure called a Pluton. A Pluton can also be referred to as a stock or a batholith, depending on the size. And so on the screen, you're seeing a picture of Stone Mountain. So Stone Mountain is considered to be one of the world's largest batholiths, and you're seeing a portion of this batholith on the top. When we talk about Pluton stocks or batholiths, we're talking about bodies of granite that cooled internally within the crust. An example of Stone Mountain, what had happened is this body of magma cooled below the Earth's surface, but there's been about 300 million years of erosion that exposes it as a dome. So we can talk about Stone Mountain and a variety of different plumes of granite that we can see in South Georgia. The next is called a sill. So a sill is a horizontal formation. So what you're imagining is that there's a crack or crevice that allows magma to come up closer to the surface, and then it flows laterally at the Earth's surface. And so a sill is a lateral formation of magma that we relate to igneous rock formation. And then the vertical component of that is going to be called a dike. So you have a fracture, and that fracture allows for magma to come up towards the Earth's surface. And so anytime that you're driving down the highway, you might look to the right or left and be able to see these formations. This is a dike complex at Stone Mountain. So I wanted to just leave you with these types of intrusions that happened below the ground, because our next lecture is going to be dedicated 100% to talking about extrusive formations that include volcanoes. And who doesn't love that? So I was a heavy definition lecture. I hope you were able to get those down. We're going to play around with those terms in the upcoming weeks. But the beautiful thing about igneous rocks is that it gives you a clue as to the temperature of the magma at crystallization, whether it cooled intrusively or extrusively, and then we can relate it to some intrusive solidification features that you will likely see throughout your lifetime. So I'm going to stop here. You've been a wonderful audience, and we'll come back at you with some volcanoes.